Tonight's Chapter 9, Metropolitan and Wide Area Network. So, like I was saying earlier, a lot of the concepts, a lot of the terms that we've talked about before, you're going to hear again tonight. Same thing with ways to improve network performance. A lot of that's going to be the exact same stuff. So, an outline introduction, it starts out with an introduction. Then we're going to talk about some of the basic types of methods for moving data across a wide area network or a metropolitan area network. These are the same concepts that we've kind of talked about earlier, but maybe we'll go into a little bit more detail tonight. Maybe it'll be a little bit clearer when we talk about it tonight. Then I'll finish this up talking about best practice in MAN and WAN design, improving MAN and WAN performance, and implications for management. So, metropolitan area networks span from 3 to 30 miles and connect backbone networks and LANs. I don't really like it whenever they put a hard figure on something like that. I think it's a bad idea. In general, it's bigger. You know, a MAN is bigger than a LAN, and a WAN is bigger than a MAN. Where's that specific measurement? That's kind of hard to say. One that covers, say, Arlington, is that a metropolitan area network? I think most people would say yeah. But if one happened to cover Dallas and Fort Worth all together, is that a metropolitan area network too? I think it probably would be, but you know, somebody else might call it a WAN. But one thing's for sure, wide area networks are larger in scope. The largest one being the internet. So a WAN can span hundreds, if not thousands of miles. So in the case of the internet, all around the globe. As you might expect, these networks are very, very large. They cross a lot of different jurisdictions, political boundaries, taxing entities, all these various different things that they cross. As a result, they're not typically built by an individual organization. They're not built by, say, strictly just by AT&T or by Microsoft or whoever. So rather than an individual organization building them, it's a series of organizations that work together. And as a consumer, we purchase services from those corporations, from those companies that provide those services. They tend to be referred to as common carriers, and we'll get to that down here in just a second. So this chapter focuses on looking at MAN and WAN architecture and the technologies associated with them from the network manager's perspective. Why the network manager's perspective? Because that's the perspective that this class is really geared towards. The network manager doesn't really have to know the integral details of how a WAN operates or how a MAN actually operates, because we're purchasing those services. But we do need to kind of have a general perspective of how they work so that we know how that our internal network will interact with that metropolitan area network or wide area network. Now, something to keep in mind, those WAN services that we're purchasing, those MAN services that we're purchasing, are regulated by various regulatory bodies. In the U.S., that happens to be the FCC. In Canada, it's the CRTC. Europe has their own version. Asia has their own version. At the state level, we have most states have some type of public utilities commission. All of these different organizations or government bodies regulate those common carriers and require them to adhere to certain specifications or certain laws, certain regulations. So as a result, if we end up having an issue with, say, AT&T, and we can't seem to get it resolved, and we feel that they're violating the FCC code, we can contact the regulatory body that's in charge, in this case the FCC, and report them to it and hopefully get it resolved that way. Ideally, you don't do that. You don't really want that adversarial relationship with your common carrier. But at the end of the day, if that's what it comes to, that's certainly an avenue that you have at your disposal. These companies are sometimes referred to as common carriers. Common carriers really can be broken into a couple different classes: local exchange carriers and inter-exchange carriers. Local exchange carriers are the ones that provide services to us as end users, the ones that we really connect to directly. Local phone companies, for example, Verizon certainly comes to mind. Inter-exchange carriers are really the ones that are linking them together. They're the ones that are providing long-distance services, for example. Sprint, AT&T, a couple of examples. So any questions so far? Okay, so in general, these common carriers are going to provide some type of circuit to us to be able to move data from point A to point B. How that data moves across the network really depends on the specific service that they provide. And those services can kind of be broken down into one of these four different categories. So either a circuit switched network, a dedicated circuit network, a packet switched network, or a virtual private network. And VPN doesn't quite fit in there quite as neatly as these other three, which can kind of more logically be grouped, but we'll get to that here in just a little bit. So in a circuit switched network, the basic architecture of a circuit switched network, we've basically got a common carrier network that sits out there, and we don't know the inner workings of it. When we send something from point A to point B, it goes into that common carrier network, and it can go virtually anywhere throughout that network. What happens is a virtual network is set up, a circuit switch network is set up, in which all our data going from point A to point B travels the exact same route for the duration of that transmission. That's why it's referred to as a circuit. So it's a temporary circuit. It's only there for the duration of that particular communication, but so it's not a permanent connection, but it is one that is set up as if it were a permanent connection. Oldest and simplest man approach, and it uses the public switch telephone network, or PSTN sometimes it's referred to as, or the telephone network, and that's provided by our common carriers. We log, for example, with dial-up networking, we log into our ISP via a modem, and a circuit is established that way. There's two basic types: POTS, plain old telephone service, and ISDN. POTS is what most people are probably familiar with, that you dial in with your modem. If you happen to be a doctor or a lawyer back in the 80s, you probably logged in with ISDN. A little bit better performance for a lot more cost. But for the masses, it wasn't particularly affordable, and the performance side of things wasn't quite there to really make it worthwhile for the masses. Plain old telephone service based circuit switch services used a regular dial-up phone lines and a modem. That was great for you as a consumer. You didn't really need any additional equipment with the exception of a modem. You didn't need a special line run to your house or anything like that. So it was something that was really relatively easy to do, relatively easy to set up and connect that way. Let's see, and they talk about WATS, wide area telephone service. Wholesale long distance services used for both voice and data. It was a way for small companies to be able to purchase large quantities of call time per month and kind of get control some of their costs in that way. Like I said earlier, ISDN was something that was used for a brief period of time. It ran into some problems. It was never really widely accepted, and it wasn't widely accepted for a variety of reasons. There were different standards, which is part of the problem. In terms of you had to have the correct equipment to work with your common carrier. So it wasn't a case of being able to buy equipment from different places and make it work together. The cost was also an issue. Like I said, it cost quite a bit more, and yet the performance wasn't quite a bit more. It really wasn't all that much better than dial-up. It did at least give you the ability to be connected and have voice communication at the same time. But again, unless you just really had a demand for that type of service, it wasn't really worth it for a lot of people. Having said all that, there were different flavors, if you will, of ISDN. That was part of the issue with respect to the different standards. There's BRI and PRI, which were basically representing different channels. PRI is basically multiple BRIs. So BRIs have 3 channels, 2 64 kilobit channels for voice or data, and then one 16 kilobit control signaling channel. PRI basically had multiple ones of these. What did that mean to you as a user? It meant you ended up having a lot more speed. It also meant you ended up with a larger bill. You also required a special circuit to be able to run PRI ISDN. Another flavor of ISDN was broadband ISDN. It was a circuit switch service, but used ATM to move data. So it used a different data link layer protocol than what traditional ISDN used. So again, this is part of the problem. You have different flavors, different types of ISDN. Some play well together, some don't, and so it was a real issue. That's why it really was not widely adopted. Circuit switch services were simple, flexible, and inexpensive. That's what we've been talking about. Very cheap to implement. A basic telephone service, at least years ago, you could probably get for around $15 a month. So it didn't really cost you all that much. Certainly appropriate when you don't have a lot of demand for a lot of data. If you're not going to require the use of the network that much, it's a good approach to take. Some of the problems with it, if you remember talking on landlines, which I guess wasn't all that long ago, and in some cases still is, but just not like it used to be. Varying qualities. You always got a lot of static in the line. In fact, you still have that issue in Mexico. That's why the cellular business in Mexico is really big. Cellular networks are big business in Mexico because the landlines are so poor that nobody wants to use them. So you have varying qualities as far as your telephone lines. The low transmission rates really make it difficult to do anything more than basic email or just some very basic web surfing. If you're going to sites like YouTube where there's video or you're downloading a lot of attachments in your email, it's not something you can really get by on. As an alternative, one good way to go is to go with a dedicated carrier or a common carrier for the user's exclusive use 24 hours a day. What they're saying is to have a dedicated circuit for your main line and then perhaps have a dial-up as your backup. And it's certainly a way to kind of protect yourself if you have a problem with your dedicated circuit, but just keep in mind you're paying for that additional circuit that you may not be using all the time. So we briefly mentioned dedicated circuits just a second. Any questions on switched networks? We're talking about circuit switched. We'll talk about packet switched here in just a second. So again, circuit switched means for the duration of a communication, that virtual circuit is that one circuit. It looks like one physical circuit, logically. Okay, so a dedicated circuit, we lease a circuit from the common carrier. We want them to dedicate a specific circuit to us. We can do that to create a point-to-point communication link between different organizational locations. Maybe an office in New York and an office in Dallas. We've got two locations that we know have a lot of need for traffic to go back and forth. We want to basically reserve that certain amount of traffic by leasing a dedicated circuit. Usually you're billed a flat rate. Say for a T1 connection, you're going to get a flat rate. It doesn't really matter how much you use that circuit. If you don't use it at all, it's still going to cost you the same amount. If you use it a lot, it's going to cost you the same amount. So if you have high network demand, this may be a good way to go. If you have low network demand, you may not be utilizing your circuit as best as you could. Requires more care in network design, and we'll come back to that here in just a second when we talk about some of the different designs, because usually if you're linking together several different locations, your design is going to impact the performance of the network as well as, if problems arise, how it's going to respond to those problems. Basic dedicated circuit architectures are ring, star, and mesh. And mesh kind of breaks down into two different architectures itself, partial mesh versus a full mesh. And the types of services that are offered for dedicated circuits, usually you're going to be talking about T-carrier service, so T1 connections, T3s, etc., and SONET services, OC1, etc. So a dedicated circuit switch. You go into the cloud, that common carrier network, and instead of just losing this connection right here and not really knowing where that circuit is, you have a dedicated circuit within that carrier network. They have devoted that circuit to you. You're paying for it. You see that a lot in, say, the alarm industry. When you set up an alarm between a business and the alarm company, you want a dedicated circuit. You don't want to have a line that might be busy because somebody happens to be calling in. make it very easy for thieves to break into places. Just call a phone number and then break in. The alarm can't call out. So dedicated lines help to alleviate that type of problem. So some of the different architectures. A ring architecture is something that you see right here. The advantage of a ring architecture, it's very similar, a lot of these architectures are very similar to what we saw in land design. Ring architecture is very simple. It's going to be the least amount of cabling that you might need for a particular design. If it's a full duplex circuit and messages can travel in both directions, if you happen to have a break between, say, Toronto and Vancouver, the message might take a little bit longer to go the other route, but you can still get from New York to Vancouver or Toronto to Vancouver just in the other direction. So it does certainly create some issues with respect to performance. If you are in New York or Toronto and you need a message to get to Los Angeles, it's really got to travel a long way. It's not going to be the most direct route in terms of being able to go as the crow flies, but it helps to reduce costs in terms of you're not leasing that many connections. A star architecture, same exact thing we've talked about at the local area network as well, and it has some of the similar advantages and disadvantages. You've still got that single point of failure there in Toronto. So if whatever devices that we're using to connect these different networks together in Toronto fails, our entire network is down. If the device is really busy, that affects the performance of our entire network. The whole network slows down. At the same time, we can have a problem at any individual location, and if that happens that connection goes down, all the other connections continue to function just like they normally would. So that's an advantage side, an advantage on the advantage side. Also, because we have direct connections, assuming we don't have a bottleneck there in Toronto, our performance is really going to be pretty good. We have direct lines of communication from site to site. It's going to be the quickest path from point A to point B for the most part on average. Downside is there's a lot of cabling involved, or a lot of connections involved. A mesh architecture is for the paranoid at heart. It's for a design where you can't afford to have a site that's not connected to the network. U.S. government comes to mind. Certainly certain e-commerce companies, that's their lifeline. That's their, if they're down, they're not making any money. So there's certain situations where you might want to go with a mesh. If a mesh is a design in which every node is connected to every other node. As you add an additional node, that creates a whole lot of additional connections. So that can get really expensive really quickly. As a result, you don't tend to see companies that go with a full mesh, rather they go with a partial mesh, where they end up with certain locations, say Toronto here again, where they end up trying to connect to a lot of different places, New York, Atlanta, Dallas, and Vancouver. Maybe they feel that that's a major connection, Toronto's a major hub. As a result, they want it to be connected to more than, say, Los Angeles or San Francisco. So those are the physical architectures. Those physical architectures have to have some kind of signaling to be able to transmit that data. What it is that represents the ones and zeros that are going across our network. T-carrier services is one of those services that they talk about in the book, and in this particular case, those are probably two of the services that they should focus on, T-services and SONA services. So T-services are very common. Most of you probably heard about T1 connections. There's other ones as well, but T1 connections, T1, also sometimes you will see it referred to as DS1. They basically refer to the hardware side of the equipment versus the actual signaling part of putting those ones and zeros on the medium.
Is this actual cable?
Pardon?
Is it actual, what is it, the T1? What are they? Is it
T1 refers to the actual hardware of the connectors and the cabling that are used for those circuits. Whereas DS1 refers to putting the ones and zeros, the data link layer of putting the ones and zeros onto the fiber optic cable.
okay, Okay, so is T1 a cable?
It's a cable. It's the connectors. That's what it's referring to, is the actual cabling and the connectors themselves. So sometimes when you're talking to people in industry, they're usually going to refer to it as T1, but you may have some people that will refer to it as DS1. They're referring to the same group of technology or clump of technology, if you will, because they work together. You don't have one without the other. You'll see the same thing here in just a second when we talk about SONET. What I really want you to know is probably T1 is 1.544 megabits per second, which is not really fast if you're talking about cable modems, but it's the equivalent of 24 dial-up channel communication channels. So you really have the ability to split things up. You can have so many channels for voice communications and so many channels for data communications. So you can really kind of get exactly what it is you want out of a T1 connection. A T2 connection is not twice as fast. It's the equivalent of 4 T1 channels. So you don't necessarily need to know these speeds. I do want you to know this speed, and I want you to know that the T2 is not just twice as much. It's more. T3 is more. T4 is more. And then something else I want you to be familiar with is the concept of a fractional T1. T1 lines are expensive. I looked those up before I came out a little while ago, and just to kind of get an idea of current pricing. And depending on where you are in the country, the company that you're dealing with, you're talking anywhere from a couple $100 a month to over $1,000 a month for a T1 connection. So if you're a small company, you might not be able to purchase an entire T1 connection. Rather, you can purchase what's referred to as a fractional T1, which might be 12 lines or 8 lines. It's part of that T1. So you can really kind of customize the connections that you really want and need coming into your business. And then kind of give you a comparison there. SONET is a competing service that you can purchase. It's a different service. It's, again, something that operates at the data link layer in our WAN and MAN environments, and allows us to, again, specify the hardware and the signaling methods of putting those ones and zeros on the medium. Uses fiber optic cable. You can get very, very high speeds. The lowest level of SONET gets you up to 51.84 megabits per second, so quite a bit faster. One subtle difference is with the SONET designation, what you'll notice is the OC1 has a data rate of 51.84 megabits per second. The numbers here actually correspond to the increases in speed. So it's a little bit different than you have for T1 connections. So OC3, for example, is 3 times the speed of an OC1 connection. 9 is 9 times it. So those are circuit switch connections so far that we've talked about. We've talked about dedicated communication lines. The next one is packet switched. Any questions on the first two yet? Yeah.
So is this dedicated circuit has anything to do with the security or?
Most people would probably consider a dedicated circuit to be the most secure. I would probably argue it's marginally more secure. So yes, there is an additional security aspect to it. I think what most people would actually argue, though, is rather than looking at it from a security perspective, they look at it from a performance perspective. That by having a dedicated circuit, you're going to be guaranteed a certain amount of bandwidth, and that's so you're not going to lose that. So if you require that dedicated bandwidth, even though everybody else is getting busy, you can still have that dedicated bandwidth. That's what I think most people would tend to focus on with respect to that. I don't think the security that you get from a dedicated circuit is going to be enough to really say, yeah, I don't think people would argue over that. I don't think it's enough additional security to say, I want dedicated over packet switched or circuit switched. So packet switch services basically take a different approach to looking at how messages go from point A to point B. Packet switch networks say we can break up a message into individual parts. That a message that we send from point A to point B isn't an entire message in itself. We can break it up into little bitty parts and send those individual parts on their way to point B, but they may or may not take the same path. And that's the idea behind a packet switch network. The reason it looks so attractive, particularly to the common carriers, is it allows them to utilize their circuits more efficiently. It allows them to shift traffic from networks that are very busy, or from channels that are very busy, to channels that are less busy, in order to more effectively, more efficiently utilize those particular channels. So with a circuit switched, a connection is established between two computers. It's solely dedicated or assigned for use only between those two computers. Data transmission provided only between those two computers, and no other transmission possible until the circuit is closed. So if those two computers aren't really talking that much, it means that circuit's not really being utilized that much. From the common carrier's perspective, they're not maximizing their use of that particular circuit. So they prefer circuit switched. It enables multiple connections to exist simultaneously. How? Go back to our local area network stuff when we were talking about packets. It labels each one of those packets with sequence numbers, with IP addresses, with port numbers. So it can go from point A, the different packets can go from point A to point B, taking different routes. Once they arrive at their destination, they're reassembled into the proper order. So again, it might look something like that. You don't particularly know the path that a packet's going to take on its trip from point A to point B. Each successive packet may take a different route. It may take the same route. Part of it depends on the protocols that are being used. So it works by, the whole concept works by interleaving packets from different messages together. So it doesn't matter that an email message along with a web request, along with an FTP request, are being sent at the same time. Those requests are not one request in and of themselves. They're individual pieces, and those individual pieces are interleaved together as they go out across the wire. Does that make sense? No? Maybe? Okay, so let's think about, we've got a network where we've got our network over here, our PC, and then we've got various routers that are all over the place. And this is the server that we're trying to log into. So when we send our first packet out, let's say it's A. A may go this route, then this route, then this route, then this route, then this route. Let's say that's an email message. Well, we may have an FTP session that occurs at the same time. Let's say F for FTP. It may go this route. It may go this route. This route. This route, etc. The next A packet may go here, 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 and then here. And it gets reassembled on this side. How? Because of the sequence numbers. The sequence numbers, those parts of the packet, become very important. That's how this side knows how to reassemble that message. If it doesn't have those sequence numbers, it doesn't know what order to put the various sequence in. If one packet arrives before the other one, it has to, one packet is going to arrive before the other one. If a packet that's further back arrives before the one that's in front, it has to sit there and wait. So it has to have memory, it has to have storage. Be able to save that packet, identify all the packets associated with a message, then reassemble it so that the application can understand it. In this case, an email program. Does that make sense? Okay. As far as the different routing methods, there's two different approaches. There's general approaches. Connectionless versus connection-oriented. With the connectionless datagram, it adds a destination and sequence number to each packet. Individual packets can follow different routes through the network. That's what we're just describing right here. That's the way a common carrier wants their network to perform. Because that means they can push data across networks that are being underutilized. So they can shift demand from their busy circuits to their less busy circuits so that they're getting better coverage. Connection-oriented creates a virtual circuit. It says, you know what, it's still a circuit, or excuse me, it's still a packet switch network, but for our particular purposes, we're going to create a virtual circuit for that particular communication so that all the packets for that particular communication travel that same exact route. That might be important for certain types of communication, video or something where you want a consistent delivery of packets across the network. So there's certain situations where you might want to create a virtual circuit or a fixed circuit across a packet switch network. So a packet switch network really gives you an awful lot of flexibility when it comes to creating different types of circuits. Packet switch versus, and it allows you to simulate a fixed circuit network as well. So, permanent virtual circuits versus switched virtual circuits. We can create in this same scenario a permanent virtual circuit which allows us to still utilize a packet switch network, and yet consistently our messages take the exact same route. Like I said earlier, you may have that situation where you have a series of computers that you know connect regularly for video communications. You want them to consistently take the same route. With that type of connection, when the application logs in and creates that initial connection, it's going to follow that route for the duration of that communication. Once you disconnect with a PVC, a permanent virtual connection, it's going to maintain that circuit even afterwards. So when you log back in with the application again, it's going to follow that exact same circuit. Switched virtual circuits, however, do that dynamically. For an individual communication, it's going to follow that one route. When you log out of that particular application and come back to it, you'll have another virtual circuit that's created, but it's likely to be a different virtual circuit. Does that make sense? I think there are kind of some subtle differences between the two. But I think if you stop and think about the names for a second, it makes more sense. If you have any questions, this is the time to ask, though. This is stuff, it's easier if you ask now, I think. Does that make sense? Okay. Data rates of virtual circuits. Users specify the rates per their PVC via negotiations. In other words, you go to your common carrier and say, I want this type of data rate. What does that mean? That means the faster the data rate, the more you pay. Or you can reduce your expectations and pay less. Generally, you're going to discuss two types of data rates. A committed information rate and a maximum allowable rate. That means they're going to provide you with at least this level of service. That's good, right? That's your minimum. This is your maximum. They don't want to give you more than your maximum. There's another term referred to as discard eligible, which basically means anything over CIR and they can drop the packet. Well, you don't really want them to drop packets. That's bad, right? Well, what it's saying, though, is when they get really busy, they're going to drop you down to this level so that they can try to accommodate the other users of the network. If it goes over this, then they're going to start dropping packets. They can't go under it because they've committed to that. But if they go over it, they have the option of dropping packets in order to accommodate other users on the network.
But if you're on max, then it will discontinue. It won't go below the...
Yeah, if you're up to the maximum allowable rate, that means that most likely there's not a lot of demand for the network at that time. And so, yeah, you can get those increased speeds. But as demand starts to increase on that particular circuit, they're going to start to scale you back and start dropping circuits until you get down to the CIR. Now, when they say dropping packets, it's not as if your data just goes off into never land. You have other layers of the protocol stack that correct for that. Remember TCP/IP? We take care of that at a higher level. We'll talk about that a little bit more here in just a second. Okay, so of the packet switched protocols, the common ones, X.25, ATM, frame relay, and Ethernet. They could do away with these top three probably and be just fine in this book. Ethernet is really the one to focus on. So I'm going to kind of gloss over those first three and talk mostly about Ethernet, but we'll just kind of touch on the other three just to kind of say that we did. X.25, very old, the oldest of the four that we're going to talk about. It's been around for quite a while, used quite a bit in Europe, not very widely used here in America. It's a reliable protocol, which means it checks for errors at the data link layer. Remember, we're talking data link layer here in the wide area network or metropolitan area network networks. So it operates basically at the same layer that Ethernet does for our local area networks. And it does that error checking. So if a packet gets transmitted and there's a problem with it, it will take care of that error by presumably retransmitting. ATM is newer. Unlike X.25, it does not provide for error checking. It forces the error checking to occur at a higher layer, TCP. It also performs encapsulation rather than translating things. So with X.25 operating at the data link layer, it has to translate when it encounters a network of a different data link layer protocol. So when it encounters a network that happens to be using Ethernet, for example, or ATM, it has to do a translation so that those two networks can talk. ATM doesn't do that. ATM uses encapsulation, which basically takes any packets outside any other types of protocols and encapsulates them into an ATM frame, transmits them across the ATM network, and then decapsulates or unpackages that packet on the other side of the network as it's passing it out to a different network. ATM provides extensive quality of service information. Because of its speed and its ability to provide quality of service information, makes it very good for things like voice communication, video communication, things like that. So here's kind of a comparison of X.25 versus ATM and how they handle errors. With X.25, when the source transmits a message to the first router, in this case of our first node on an X.25 network, an error check is done. If the network, if the frame is okay, it'll go ahead and transmit it to the next step. If it's not, it's going to correct it immediately. At the next step, it's going to transmit it to C. If it's okay, it's going to go ahead and transmit it to D. If not, it's going to go back to B and say, hey, retransmit that. That one's damaged. It does that process for each step. Well, that creates a certain amount of overhead. As a result, X.25 doesn't perform as well. ATM, on the other hand, does not do any error checking. So instead of having to check at B and check at C and check at D, it just forwards it. Well, as long as the frame is okay, that's great. That means it's performing better. When it gets all the way down to here to E, what does it do? It passes that message up the protocol stack, through ATM, up the through IP to TCP. TCP says, hey, wait a minute. This packet's damaged. We got to send it back and get a replacement. So then you have to go all the way back through all those different steps to get it. So assuming your network is working well, you're not generating a lot of bad data, a lot of bad packets, ATM performs much, much better. And the reality is, in modern networks, that tends to be the case. In older networks, this was probably a better approach. They talk about ATM features. I'm not that worried about all that, but what I did want you to focus on is that ATM, as far as the data rates, is really pretty good. ATM performs very well, does not offer error control, and it tends to be very scalable, meaning we can add more and more to our ATM network, and it still continues to perform very well. Frame relay is another data link layer protocol that operates across our WANs and MANs. It also encapsulates packets just like ATM. Like ATM, it's also unreliable, which means if you have the potential to transmit bad packets or bad frames, and rely on other layers to correct that. Unlike ATM, it does, at least natively, it did not support quality of service. That's no longer true. A frame relay does now support quality of service, which means you can transmit video, for example, across a frame relay network and get good results. Speeds are on the low end, not all that great, but on the higher end, not that bad. Really depends on your needs as an organization as to whether or not that will suffice. 45 meg for a small company is probably sufficient. For a major corporation, it's probably not. And then the one that they probably should have focused on, Ethernet services. This is something they come back to at the end of the chapter as well. The idea is you want to make things for a network manager as easy as you can. It's easier to standardize on equipment. It's easier to standardize on protocols. Why not have the same protocol at your local area network layer as you have at your backbone layer as you have at your WAN or MAN layer? It just makes things easier in terms of the design and maintenance of the network. So most organizations today are going to use Ethernet and IP in the LAN and the backbone network, and it's becoming much, much more common in the WAN and MAN environment. They talk about speeds currently being from 1 meg to 1 gig. I would suggest it's today probably between 1 gig and 10 gig, much better, and you're seeing some even hit 40 gig. An advantage, like I was saying a second ago, an advantage to having Ethernet in your WAN environment is there's no need to translate, do any translations, there's no need to encapsulate. All of that adds overhead, all of that adds processing time, which slows down your network. So it's definitely an advantage to use that same data link layer protocol in your WAN and MAN environment. They do mention that it's an emerging technology, so expect changes. That's certainly true of any emerging technology, that you can expect there to be changes in the implementation of the standard. It makes it troublesome for a network manager to take advantage of the latest and greatest technology, because if you do, you're likely to encounter some of the bugs that they didn't discover as they were rushing a particular product to market. Having said that, Ethernet at this level has been out for a while now, since the publication of this book, and it's something that's performed very well at the local area network layer. I would certainly feel very comfortable with a common carrier that used Ethernet as their data link layer protocol. The last one that, is any questions over that? Okay. Virtual private network. The last one, like I said, this one doesn't particularly fit in real well with packet switch versus circuit switch, but it kind of does. It is kind of related, and so they kind of threw it in here. Provides the equivalent of a private packet switch network over a public internet. Why would we want to do that? Well, the internet's cheap. It's cheap to access the internet. So if we can privatize our data somehow to get it from point A to point B in a safe and secure way, we have the advantages of having a very expensive circuit without having to spend all that money for it. And so that's the idea behind a private packet, a virtual private network. So it provides low cost and flexibility, uses the internet, and is relatively easy to set up and configure. Disadvantages: unpredictability of internet traffic. So because we're depending on the internet for our connectivity, we don't have a dedicated circuit. If the network happens to get busy, we might have problems with our VPN. There's also a lack of standards. There's different technologies that implement VPNs, and there's not a lot of standardization amongst those various softwares and hardware products. As a result, sometimes those various hardwares and softwares don't play nice together, so sometimes you can have problems with respect to that. You might have to get locked into a particular vendor, which, you know, if that vendor stays in business and supports their product well, that's great. If they don't, that's, you know, you've kind of sunk that investment. So conceptually, it kind of works like this. On one side of the connection, you have your company network, their backbone, and some type of VPN gateway. That's what's going to establish that connection through the internet to a VPN gateway at another facility. This tube right here, if you will, that has your connection going in between it, is supposed to represent basically an encrypted communication. So what it does is it takes your normal network traffic, just like these two networks are directly connected, takes your normal network traffic, encapsulates that, and encrypts the contents of it, and then sends it across the internet just like it were any other TCP IP packet. Sends it right across. If anybody happens to intercept it, they go to open the contents of the IP packet. What do they see? They see an encrypted payload, so they can't do anything with it. Then on the receiving side, it strips that IP packet down and gets down to the VPN code, or the encrypted payload, then has to decrypt it, which adds overhead, but you now have a secure way of sending information from point A to point B. So if you want to look at it from the packet perspective, your network software does everything just like it normally would. You put in a request for a web page, http://www.microsoft.com. It sends it down to the TCP layer, it sends it down to the IP layer, and then it gets sent to the VPN software, where it gets encrypted and then processed just like a normal packet would. It's sent across over here, and then goes through the reverse process and breaks it down back to the payload, and then does the decryption on it. And another representation of that, if you will. Any questions over that? There's still more on it, but make sure that people conceptually you got that? Okay. VPN types are really pretty flexible, or VPNs are really pretty flexible, so you can apply them in a variety of different contexts. They list three here: an intranet VPN, an extranet VPN, and an access VPN. An intranet VPN is appropriate when you happen to have offices that you want to be able to communicate securely from fixed locations. You have an office in, like I said earlier, in Dallas and in New York. You want to allow them to communicate securely across the internet, where you don't have to worry about if somebody happens to be listening in on the wire. So you can purchase the hardware, because hardware performs better than software, and have a connection a VPN connection between those two sites that allows them to communicate securely. You can also generate an extranet VPN, which is essentially the same thing. It just allows external vendors to log into your network and be able to access information across a secure connection. An access VPN, though, is a little bit different. An access VPN relies, at least, more substantially on software. But the trade-off for that is it gives you more mobility. So if you have traveling salesmen, you have people that are out in the field going from point A to point B to point C, sometimes are accessing your network from a hotel room, sometimes from a client's office, so from a variety of different locations. If they need to be able to log back into the corporate network securely, they can use an access VPN in order to be able to do that. It may be something as simple as a web browser that they log into that sets up that VPN connection between their laptop and the corporate network. And again, it encrypts all that data going back and forth at that point. So it really depends on the needs that you have as to the type of VPN that you want to set up. Design practices. Difficult to recommend best practices. Why? Because you're not really buying products. It's not like at a local area network level where you can say, let's buy a better router, let's buy more switches and replace some of these routers with better performing switches. We don't have that situation with WAN design. We're purchasing a service from a vendor. Certainly you can go from one vendor to another, but again, it's not like a switch. There's lots of different vendors that sell switches. There's not a lot of common carriers that exist. Another thing that adds to the difficulty of this, the environment's always changing. I mean, you always hear about if you purchase a computer today, it's obsolete tomorrow. Well, it's no different when you start talking about telecommunication networks too. The speed with which they change, the competitors that enter and leave the market is always very volatile, so it's always changing. One thing you can do to try to make some sense or make some decisions based on the different networks that you might be considering, the different designs you might be considering, are the effective data rates and cost. So how fast? SONET provides better speeds than T connections. It just does. But it costs more. So is it worth that additional cost? Reliability. Which one is better as far as reliability? Not just in terms of your network, but also in terms of the carriers that you happen to be using. Look at those different carriers that are available that you have as an option, which hopefully is more than one, may not be, but see how responsive they are when the network goes down, and how quickly do they respond, and how easily does their WAN integrate with your network. Certainly if they're using Ethernet, that's going to make that integration a little bit easier than if they're using one of the other data link layer protocols. Ethernet just makes things easier if you're using it at all the different layers. Design practices start with flexible packet switch service. In other words, if you're a small company and you don't have a lot of funds, packet switch services, access to packet switch services is a lot cheaper. DSL is an example of packet switch services. Cable modems, packet switch services. So it's a lot cheaper. It's a way for you to share the network connections with other users. Because those lines are being more efficiently used, your rate, the common carrier has a lower rates for you. They're able to distribute those costs amongst all the various users. If you need a dedicated service, though, you're paying for the use of that entire circuit. So unless you have a need for a dedicated amount of bandwidth, you don't quite want to move there until you get to that point. And then if you're particularly paranoid and you really have to make sure you've got a backup, maybe you do both. You purchase a dedicated circuit for the bulk of your communications, and then have a circuit switch network in case demand rises above the capacity of your fixed line. Then they kind of give you a comparison table of all the various services and relative cost, reliability, and network integration. For my bang for the buck, I would stick with Ethernet whenever you can. And I'm really surprised they don't push it. I'm really surprised they don't push it more in the book. It may be due to the age of the book. Not that it's that old of a book, because it's really not. But 4 years in networking is quite a bit of time. So I believe that book's about 4 years old. It may not even be that old. So best band LAN practices, low traffic needs. Certainly dial-up. If you're only going to download a message every now and then, you're going to log into a news group, dial-up's perfectly fine for that. Moderate traffic needs, VPN if reliability is less important. Why? Quality of service, things like that. T1 if the network volume is stable and predictable and frame rate otherwise. If high traffic needs, Ethernet if available. Just, again, because of all the advantages that Ethernet gives you. And then with very high traffic needs, Ethernet if available. I would probably still stick with Ethernet whenever you could. But then otherwise SONET or ATM if you have to. Improving performance, it's exactly the same as we've seen before. Devices on the network, upgrading the circuits, and changing demand. Those are the three, the specifics of those three may change slightly from one to the other, but conceptually, it's exactly the same. Checking the devices on the network, higher speed devices, higher speed computers, etc. upgrading the circuits, so going from a T1 to a SONET, and by changing demand placed on the network, so shifting it to other time periods. So the devices, maybe we have the opportunity to upgrade routers and computers that happen to exist on the network. We want to find devices with lower latency. What does lower latency mean? That means the device doesn't hold on to the data as quickly or as much. So it starts transmitting that data much more quickly. Low latency is good. We could also examine the routing protocols, whether or not we're using static or dynamic. Dynamic routing increases the performance of networks with lots of possible routes. But if we don't have a lot of different routes, we probably want to use static routing. Circuit capacity, this is what I was talking about just a second ago. If we're using a T1 connection and we're finding ourselves being overloaded, maybe we want to go to a T3. Maybe we want to go to a SONET network. It just depends on the demands, how much is our current connection, our current circuit underperforming. Reducing network demand. What are the applications that you're running on the network? Shift network usage. Use data compression if you can, which is really pretty common when you're talking about communication networks. And potentially redesign the network. Move data closer to applications and people who use them. We'll see that again next week on the chapter on the internet. Some of the techniques that companies use to move data closer to their users, whether it be customers or it be people internal to the corporation. There's a couple of different techniques that we'll talk about. For example, we can use distributed databases to spread traffic access. For example, if we happen to have two locations, one in Los Angeles and one in New York, we could have the one in New York have half the database. They have all the customers that are in the eastern half of the U.S. and the other half of the database located in Los Angeles for all the people in the west half of the country. What does that do? Well, that means now all of a sudden, if before the database was entirely located in New York, any time a customer had to be accessed from Los Angeles, they had to go across an entire network to be able to access that data. By splitting that, you've reduced the demand on that WAN connection from Los Angeles to New York roughly in two. Any questions? Implications for management. Changing role of network and telecom managers. Increased and mostly digitized data transmission causing the merger of these positions. Whereas at one point in time, organizations had two departments. They had a datacom, they had a telecom department within their organization to manage their computer networks and their telephone networks. That's being blurred. You're seeing an integration between those two departments. What does that mean? That means reduced staff, more responsibility for that reduced staff. But also means better utilization of their investment, so that their communication lines are being more heavily utilized. Changing technology is another implication for management. They say within 5 years, X.25 and ATM possibly might disappear. I'd say this is dated because that's certainly the case. In fact, I would even throw frame relay into that as well. VPNs are certainly a big part of the current way of thinking for a lot of corporations, because they can take advantage of cheap access to the internet and still have secure communications. And Ethernet is certainly becoming the dominant data link protocol at the WAN environment, or in the WAN environment. And decreasing costs, not COTS. I didn't type this. Although I could certainly do a typo. Costs of setting up MANs and WANs, it's getting cheaper and cheaper. Just like the rest of technology, costs are coming down, and that's not something that's going to change. What you will see in order to maintain profit margins of these telecommunication companies is, instead of reducing the cost too much, you'll see additional features that come out. So higher speeds, additional features in order to be able to charge premiums for those services. But you'll see the basic costs of Ethernet access, for example, come down. Also changing vendor profiles. Much like the marriage between datacom and telecom, you see a lot of these vendors that are doing the same thing. You see telecommunication companies producing datacom equipment, datacom companies producing telecom equipment. And so you see a lot of these companies that typically you would have associated with telephones producing datacom equipment, and their equipment being sold to corporations. So the lines are being blurred between a lot of these players. Probably a good example at the consumer level is, think about Verizon, that offers television service now. That's not something that you would have gotten several years ago. They do telephone calls. So any questions over that chapter? I think that's a pretty good chapter, and I think it kind of hopefully helps to sum up some of the other chapters in terms of the use of similar concepts and things like that. That's the last chapter that we have on that type of stuff.
Well, looking at the outline, what possible exam questions, or what should we really focus on in here? Because last chapter, okay, it was slightly difficult, but I don't know. I think I found this one a little bit more.
Okay. Things that I would be interested in would be things like, I would want you to know what a mesh network is versus a partial mesh network is.
Okay.
I would want you to know, we kind of come back through some of these slides. Certainly, the three things to handle performance, which, like I've said before, and the other things, these general categories, you should pretty much have down by heart. So checking the devices in the network, making sure the devices are performing as well as they can. If you have a switch that's performing poorly, a faster switch, a better quality switch might perform better. Upgrading the circuits and shifting demand. Those are the three things that you're normally going to see. I'd want you to think about things like design practices. Some of these factors of being able to compare which particular service is better. How do you go about doing that? Well, look at the data rates and costs. That's certainly one that makes sense. I think all these make sense, but I want you to be able to think about those and be able to discuss them, why they're important, if there were say, an exam question on it. And the reason that those are important is because it's a service, not a product. Probably ought to have a general idea of intranet, extranet, and access VPN, what the differences are between those three. I'd want you to conceptually know what a VPN is. I don't expect you to be able to talk about the individual parts of the packet. This isn't a computer science class.
Thank you.
But I would want you to understand what a VPN and why it adds value to a company, which is it allows you cheap access to a secure network. Cheap being the access to the internet, secure due to the encryption. I'd want you to probably be able to focus on, it talks about how we have different data link layer protocols in a packet switch network at the WAN and MAN environment. I'd want you to really kind of focus on Ethernet. You probably ought to know the names of the others, but other than the high points that I hit, I wouldn't worry about the other stuff. So for example, when we talked about X.25 being a reliable protocol, that I would want you to know. This stuff up here, LAPB and PLP protocols, don't worry about that. But X.25 being reliable, yes. ATM, this stuff right in here, performs encapsulation and provides no error control, and QoS. So if you were to see this without the text up there, I'd want you to be able to say what's happening. I'd want you to be able to compare packet switched versus circuit switched versus dedicated circuits, and connection oriented versus connectionless. some definitions. POTS, what a plain old telephone service is. PSTN, Public Switch Telephone Network. Common carriers, local exchange carriers versus inter-exchange carriers. And then don't get hung up on it, but know the distinction between a MAN and a WAN. Like I said, I don't like the idea that the authors took with respect to associating a specific mileage distinction. I think that's troublesome. But conceptually, they're on target. As long as you don't think of those as hard numbers, you think of those as ballpark numbers, it's not a bad definition.